Alright, dear participants of online ICWE conference, I'm about to give the presentation of our paper entitled I Don't Have That Much Data, Reason User Behavior Models for Websites from Different Domains. This is a full paper resulting from a cooperation of several co-authors. My name is Bakaev from Novosibirsk State Technical University, Russia, and my colleagues are from Germany. So, a few words about motivation of our research. Well, evaluation of user interfaces became widely popular already in the early 90s, and still it's a hot topic. But meanwhile, web user interfaces become more and more sophisticated. And an example is we can see from the internet Wayback Machine is the website for the University of Helsinki. That's how it looked in the year 2000. And then 10 years later, and then nowadays. So you can see the difference. Correspondingly, the complexity of setting up and analyzing the assessments of user interfaces also increases. Okay, then academic sources say that user tests are the most effective method of UI assessment, but in the industry, they don't always use it. Often it's substituted with A/B tests. They have their advantages, but they're clearly not suited well for determining such things as usability or user experience. Well, at the same time, no one, either in academia or in the industry, doubts that efficient evaluation of user interfaces is good because it leads to better interfaces and higher acceptance of the product by the users. And from recently, there is a way actually to avoid interacting with real people, which is user behavior models. Among other things, they can predict subjective parameters in interaction. And this can be done from previous interactions, from the actual UI, if we analyze some static or dynamic properties of it. And the advantage is once you train the model, you can apply it repeatedly. Now, a few words about user behavior models. They kind of mainstream and artificial intelligence applied in human-computer interaction nowadays. And there are different types of the models. What they have in common is the input, which is twofold. First, their specification of the interaction context, which also includes the target user. And second, the specification of the actual user interface being evaluated. And they have the output, which is a certain quality attribute like some measured thing, time, success rate, and so on, or some subjective impression the user would have. They are trained with the data that you collect from real or staged interactions with users, and often you need quite a lot of data for training actually, and if it involves humans it's not so easy to get. So naturally, once we have the model, we want to use and reuse it and evaluate different versions of UIs in our project or maybe in different projects. So the research problem in our paper is tailored to web engineering. The question is, can such trained models predict for a large range of websites of different domains? And if so, does the distance between the domains have an effect? And in our research, we used over 3,000 websites from 7 domains, like universities, museums, computer games, and so on. And we built several artificial neural network models and made comparisons between them. For that, we used the mean squared error as the quality index for the models. And the subjective impressions that they predicted were complexity, aesthetics, and orderliness. And the training data was collected from 100-something users. Now, a few more words about our approach. In a way, it's similar to transfer learning, but we are somehow more radical. Instead of having the final fine training step for the pre-trained model, we just apply the models of one domain, which we call the native, to the others, the foreign. And the all popular CNNs are not particularly suited to deal with user interfaces, so we needed some feature-based representation of web UIs. For that, we used the tool which we once presented in ICWE 2 years ago. It's a visual analyzer. Actually, now it has become several visual analyzers, which take a website screenshot and output quantitative metrics for it. Actually, there are quite a lot of metrics, but we used 32 of them for the reasons that we list in the paper. And since collecting lots of data that involves humans is costly, we wanted to minimize the model's requirements towards the training data. Fortunately, we were not interested much in the actual quality of the models, but in the relative prediction accuracy. So the models in our study were just simple linear regression INNs. And we decided that for each domain we need over 300 websites at least. The visual analyzer that has become the Web UI measurement platform is presented in this slide. The platform now integrates UI metrics provided from various remote services. The two main ones are the one we developed together with the Technical University of Chemnitz, and the other is developed by the team from Aalto University, Finland, and actually it provides more metrics. The input is a web page address or a screenshot, and the platform, depending on the set of metrics that you specify, sends requests to the remote services. It then receives back the values for the metrics and saves them into the database for further analysis. You can actually try how the platform works. You can see the address here. Fortunately, we recently implemented batch mode for the platform, so we didn't have to upload the 3000 screenshots by hand. I have to say, however, that the services failed to produce the metrics for about 10% of the screenshots. For some reason, the white space metric was the most problematic, so that value just never came back from the services, and we are not sure about the reason. So we had to exclude the screenshots with the complete set of metrics from the analysis. But more on the analysis I will tell later. In this slide you can see the 7 domains that we used in our study. We wanted them to be kind of on the same level of generality, and also that the pairwise semantic distances between them are different. So these were culture, food, computer games, government and society websites, health, news, and universities. The numbers in the brackets that you see show how many home pages were used to make the screenshots for each domain. And these pages had to be in English, and they had to have diverse visual designs. And the collection was done by our student volunteers. So we thank them very much. And then we used the visual analyzer to process each of the screenshots. After all, for each of the screenshots, we had 32 quantitative values, as you can see in the list of metrics. And as I said before, the screenshots which didn't have the complete set of values had to be removed. And in this slide, we present our measure of distance between the domains. We relied on archive of Demos catalog and mapped our domains to its categories. For all the domains except culture and the government, the mappings were direct. For the latter two, we had to kind of average the categories, as shown in the diagram. And then for each pair of the domains, we calculated the distances. Basically, they corresponded to the number of steps in the shortest path between the two nodes in Demos hierarchy. This slide has the information about the users who provided the subjective evaluations that we used to train the models. The participants were mostly from Russia, many of them students of my university. Also, there were people from Bulgaria, Germany, and so on. The total number of participants was 137. They were mostly rather young, as you can see. And there were 3 scales for the subjective impressions: complexity, aesthetics, and oddliness. For each of them, the users would provide their ratings from 1, which is low degree, to 7, which is high. And to present the screenshots and to collect the evaluations, we used an online survey tool that we specially developed. The screenshots were presented in the randomized order, but we controlled the number of evaluations for each screenshot. We wanted to be more or less equal. And each participant was asked to evaluate 100 screenshots, but a few of them came for more. And this is the details on how we implemented the artificial neural network models. We used Colab, the free tool provided by Google. The architecture of the model is presented in the code. It basically had 3 layers, and the loss function was mean squared error. The test set was 20% of the whole dataset, and the validation set was 20% of what's remained. We also used the early stopping mechanism and would select the best models among all the epochs. Here I'd also like to know that we introduced the relative mean square error as a ratio between the current models MSE and the MSE for the native model for this domain, which we understandably use as the baseline. In our data analysis, we worked with the two hypotheses. First, that there are significant differences in the quality of the models due to the website's domain. And second, that the difference is smaller for more similar domains and larger for more distant ones. As I said before, we had to exclude about 10% of the screenshots from the analysis, but the remaining number was still quite high, over 3,000. On average, each screenshot was evaluated by about 5 participants. We started with the correlation analysis, for which we used Kendall's tau, that's non-parametric statistics for ordinal scales. And it turned out that complexity and aesthetics, as well as aesthetics and orderliness, were significantly correlated, whereas complexity and orderliness were not, which we did not quite expect actually. Now, this huge table shows the absolute and the relative mean squared errors. The latter are shown as the percentages. There is each possible combination of the native and the foreign domains. What it means is basically we trained the model on the data for example, culture websites, and then validated it on the dataset of food-related websites. And it turned out that the MSE was 40% worse in this case, as you can see in the second cell of the table. The MSEs for the native models are on the main diagonal, so they are the baselines for their rows. The resulting value in the table of 123 means that on average the foreign models for complexity were 23% worse than the native ones. In this slide you can see the same table for aesthetics, and also the resulting value of 160% means that the foreign models were 60% worse than the native ones for this scale. And finally, the same table for the orderliness scale. As you can see here, the value is 145%, which is somewhere in between the complexity and the aesthetics. But of course, statistically speaking, 23% can be a lot or can be insignificant. So we used t-tests to check for significance of differences in mean squared errors for native and for foreign models. It turned out that the difference for complexity was not significant, but for aesthetics and for orderliness it was rather highly significant. So that was relevant for our hypothesis 1. As for the hypothesis 2, where we wanted to test our measures of distance, we calculated percent correlations between the distances that we calculated earlier and the relative MSEs. We found that they were significant for aesthetics and orderliness only. Further, we tried to build regression with dummy variables. It means that, for example, scale A has the value of 1 if the model relates for aesthetics scale and 0 otherwise. We found that the regression equation you can see in the slide was highly significant, but the R-square was not that high. Finally, we decided to test the effect of the dataset size. The correlation between the model's MSEs, average per domain, and the available dataset size was not significant. That's good news actually, because it suggests that our models didn't have underfitting or overfitting. But the next question was, what happens if we just pull together the data for all the domains in just one huge dataset? And we tried that, and it turned out that such models were superior even to the native models trained on domain-specific datasets. So we can only say that the unreasonable effectiveness of data is confirmed in our study. But on the other hand, as you can see in the slide, the improvements due to using domain-specific datasets compared to the foreign ones were also rather comparable. So, concluding, the key takeaways are the following. More data is always better, but it's not free if we talk about user interactions. The hypothesis 1 was confirmed for 2 scales, but difference for complexity was not significant. It probably implies that the perception of complexity is independent of the website domain, but the perception of aesthetics is domain dependent. The measure of distance that we proposed and tested in hypothesis 2 did have an effect. We can very roughly say that an extra point of distance adds 8.4% to the model's error. The limitations of our study include rather low accuracy of the models and rather narrow group of employed users. Our plans for further research implies close investigation of both the domain distance and the subjective impression scales. Thank you.